Hello students, good time to all. I am Chandan Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss applications of Gauss law. One of the application that is electric field due to uniformly charged spherical shell. Let's begin. There are various applications of Gauss law, but here one application is studied throughout that video lecture, that is electric field due to uniformly charged spherical shell. Gauss law is extremely useful in dealing with electrostatic problems. The solution of certain problems become very easy by use that law. So here spherical shell means a hollow sphere of infinitely small thickness is known as the spherical shell. Now considering a uniformly charged spherical shell, of radius capital R and its center at O. Let Q is the total charge on that of sphere. Total charge on that of sphere is small q. And we have to calculate the electric field due to that charged spherical shell will be spherically symmetric and radially outward. The electric field due to that of charged symmetrically spherical shell, and we have to calculate the electric field intensity due to that charged symmetrically charged spherical shell at the point which is outside that of spherical shell and the point on that of surface and also within that of spherical shell. So there will be three possible cases, and we have to calculate the electric field intensity due to that uniformly charged spherical shells in these three possible cases. First case 1, when the point, let that point be the P which is outside the charged spherical shell. At point P outside the charged spherical shell, So to do so, let me take the point P lies at a distance r smaller from that of center O, and we draw a sphere of radius r. By taking the radius r, we draw the sphere and center at O, as that is the that one be the Gaussian surface. That one be the Gaussian surface. Let the point P will be on that of Gaussian surface. Here is the point P on that of Gaussian surface. This is the spherical one. Imagine in case of 3D to that of Gaussian surface. Let we have to calculate the electric field intensity at point P due to that of charged spherical shell Q. So here at that point let E vector be the electric field intensity at point P due to the charged spherical shell that is E vector, and that electric field intensity that is 1 by 4 pi epsilon naught, that is permittivity of free space, Q divided by R square, Q divided by R square. Now we consider the small area element ds on that of Gaussian surface, small area element, that is ds on that of Gaussian surface, and since the electric field are outward, radially outward, so that is the direction of that of electric field intensity E, and also the direction of ds vector means E vector and ds vector are parallel with each other. We consider the point P, means the consider small area element ds vector of that of Gaussian surface around that point P, and let we define a term, that is surface charge density of that of spherical shell sigma be the surface charge density of spherical shell. That is charge by surface area, that is charge Q divided by surface area 4 pi R square. Here we can get the Q in terms of surface charge density, that is 4 pi sigma R square, 4 pi sigma R square. Since the electric field intensity E vector at every point of that of Gaussian surface is directed radially outward, therefore E vector and ds vector will be parallel. Both electric field intensity and ds vector at point P will in the same direction. Now we calculate the total flux passing through that of Gaussian surface according to Gauss law. According to Gauss law, total electric flux passing through Gaussian surface according to Gauss law, total electric flux passing through that of Gaussian surface, that is phi is equal to closed surface integration over S E dot ds is equal to Q divided by epsilon naught. Therefore, E dot ds closed curve integration over S, that is E ds cos 0 degree is equal to Q by epsilon naught, as E vector is parallel with that of ds vector. Therefore, the angle between them is 0 degree, that is E ds closed curve surface integration over S, E ds is equal to Q divided by epsilon naught, or the value of E is put here. Here the electric field intensity at that point P due to that of charge spherical cell, that is 1 by 4 pi epsilon naught Q by r square. Electric field intensity, that is the magnitude of E. So, put the value here. First, E is the constant term, that is E to that of outside, closed curve integration over S ds is equal to Q by epsilon naught, or E is equal to E into closed curve integration over ds. This is the ds section, that the value will be 4 pi r square. Total area, total surface area, that is 4 pi r square is equal to Q divided by epsilon naught, or E is equal to look at that expression, E is equal to yes, E is equal to 1 by 4 pi r square Q divided by epsilon naught. Okay. Not that term, that is just the electric field intensity at point P due to that of charged spherical cell. That mathematical expression is not needed here. Okay, we have to calculate the electric field intensity at that point. So, here 1 by 4 pi r square Q by epsilon naught, the value of Q is put here. So, E is equal to 1 by 4 pi epsilon naught, the value of Q 4 pi sigma r square, 4 pi sigma r square divided by small r square. 4 pi cancel out, the result will be E is equal to sigma r square divided by epsilon naught small r square. This is the mathematical expression. The electric field intensity outside that charged spherical cell, as if whole charge is concentrated at the center and E is directed outward. Okay, that is the expression for electric field intensity where the point P lies outside that of charged spherical cell. we can easily calculate by using Gauss law. This is case number 1. Again, for case number 2, when that point lie on the surface. Case number 2, case 2, at point P on the surface of charged spherical cell. Then what should be the value of electric field intensity? Let here we take that point P lies on the surface of that of charged spherical cell, means capital R is equal to small r, and here we draw a sphere of radius r and taking the center as O as the Gaussian surface, means that spherical surface is also treated as the Gaussian surface, and in this case the Gaussian surface passing through that point P will coincide with that of charged spherical cell. Here r is equal to r, small r is equal to capital R. Here r is equal to r. Therefore, according to Gauss law, the total electric flux passing through the Gaussian surface that is phi is equal to closed surface integration over S E dot ds, that is q divided by epsilon naught. Again E vector and ds vector are parallel with each other, therefore E dot ds, that is E ds cos 0 is equal to 1, E ds is equal to q by epsilon naught, E to that of outside E closed curve integration over S ds is equal to q by epsilon naught, or E into total surface area, that is 4 pi capital R square q divided by epsilon naught, or E is equal to 1 by 4 pi R square q divided by epsilon naught. As we know the value of q according to the definition of surface charge density, the value of q 4 pi sigma R square, here we put that value, or E is equal to 1 by 4 pi epsilon naught in place of q, that is 4 pi sigma R square divided by R square. Here 4 pi cancel out, R square cancel out. Electric field intensity E is equal to sigma divided by epsilon naught. This is the electric field intensity at that of point P, where the point P lie on that of charged sphere. This is case number 2. Next, case number 3, when that point lie inside that of charged sphere, then what happened? Case number 3, at point P inside the charged spherical cell, Here let the point P lies inside that of charged spherical cell at a distance of small r from that of center. Here that P lies inside that of spherical cell. in that of case that small r is less than capital R, and draw that of Gaussian surface as a sphere of radius small r and the center O passing through that of point P. Here inside that of spherical shell we draw the Gaussian surface having the radius small r at the center, taking O as the center. Then according to Gauss law we apply Gauss law here as you take that of Gaussian surface. So according to Gauss law, the total electric flux passing through that of Gaussian surface that is phi is equal to closed surface integration over E dot ds is equal to charge enclosed, that will be 0 divided by epsilon naught, where q is equal to 0 inside the closed surface. Since charge distributed on the surface, not in the surface. That is the reason the value of q will be 0. Here E dot ds, similarly these two are parallel, that is why the angle will be 0. Here E ds is equal to 0, again e to that of outside closed curve integration over s ds is equal to 0, or E 4 pi r square is equal to 0, or E is equal to 0. And the electric field intensity inside that of spherical shell will be 0. Here we discuss 3 possible cases, that the electric field due to that of uniformly charged spherical shell when that point is outside that of spherical shell, when that point lie on that of surface, and finally inside that of spherical shell. By taking 3 possible cases, we can draw the graph as electric field intensity. If we draw the graph between electric field intensity along y axis and distance along x direction. So what happened here? At the distance capital R, means the point lie within that of spherical shell, the electric field intensity will be 0. But when within that of R, capital R, the electric field intensity will be 0. But on that of surface, means at distance capital R, the electric field intensity will be maximum. At that point the electric field intensity will be maximum, and gradually outside that of surface, gradually the electric field intensity decreases. That is the graphical view how electric field intensity varies with the distance. This graph indicates the variation of electric field intensity E due to the charged spherical shell. So with the help of this video lecture, we understand one of the application of Gauss law, that is electric field due to uniformly charged spherical shell, case number 1. Then case number 2, Last one, that is case number 3, on graphical view, how E varies with distance of that of charged spherical shell. So, with this useful and informative notes, let me wind up this session. Thank you.